Okay, so in this video, I'm going to take this os struct, os stuff that we made in the previous video, and I'm going to turn it into a more complex program. So first thing I'm going to do is I'm going to change this back to a sine wave. So it's going to be getting a sine wave. And we're going to get rid of the sync interpolation. So we're going to go back to linear interpolation. We don't need any oversampling, so I'm just going to get rid of that. Okay, so now we just have a basic oscillator, and it has linear interpolation, just a sine wave oscillator. And yeah, so right now, let's make the frequency, instead of being using the mouse, we're just not going to use the mouse. So we're just going to say the frequency is maybe 100, and we're going to get rid of the lag. Okay, so back to a simpler program, and we can get rid of that lag and get rid of that lag. It doesn't really hurt anything, but the fewer things you have lying around, probably the better. So let's go back and play this. Right, so we just have a sine wave oscillator. Okay, so first thing I'm going to do here is I'm going to make give this oscillator a modulating oscillator, right? So I'm going to say var mod, and the modulator is going to be just like this oscillator. So I'm going to copy and paste that. Okay, so basically now we have two oscillators. We have a modulating oscillator and this oscillator that we're going to hear. So let's give the modulating oscillator a frequency, let's say maybe 0.5. So the modulator is going to be self.mod.next. And in this next function, we need to give it the frequency. So we're going to say mod freak. Okay, so that's just a slow moving oscillator. We can actually make it a little slower. And notice that this is underlined yellow. It's because it's not being used. So, but we're going to use it. So we're going to, let's make a variable called out, and the out is going to be the sine wave oscillator, and we're going to multiply it by the modulator. So that should just make the volume of the oscillator go up and down, and now we can return out, right? So we have a modulator, it's slowly moving up and down, that it's basically going from 0 to 1 to 0 to -1 to 0 to 1 to 0 to -1. And then we're multiplying the output of this oscillator by that. So we should have this oscillator. We should hear this going up and down at this volume. So let's give that a shot. Okay, so we hear it. The volume is going up and down. So what I want to do is I want to make I want to also pan it. So we're going to add another oscillator, actually, pan os. And the pan os is just going to be like these other ones, linear sine wave. Okay, so now we're going to have a pan oscillator that's panning back and forth. So pan freak, we'll say it's 0.5. 1, and pan val equals self.panOs at panFreak. Okay, and so, dot next, panFreak. So it's yellow again because we're not using it, but we are going to use it. So here is our output, and notice that output is a float 64. So we're going to use a function down here called pan. So now we're going to say out2, and is going to be pan2, and that is our panning function. Pan2 is not a struct, it's just a function. So it's missing 2 arguments, samples and pan. So if we say the samples that we're panning are out, and the pan is pan val. So yeah, so if you hover over this, it's expecting samples and pan is between -1 and 1, which is the output of the oscillator. So we have an oscillator going from -1 to 1, -1 to 1, -1 to 1, very slowly, once every 10 seconds. And pan 2 is taking that output and then using this to pan it, using this to be the where it is in the left and the right. Now, if you look at pan 2, the input is a float 64 samples, float 64, which is what out is, but the output is a SIMD float 64.2. What does that mean? Well, that is a 2-channel, basically a 2-channel variable. So this variable now has 2 channels. As I said in the other videos, SIMD vectors need to be a power of 2. Since we're dealing with audio, that's mostly pretty easy to deal with, right? Because usually you're dealing with 1 or 2 channel signals, though you can obviously deal with other kinds of signals. So in this case, pan 2, because it is panning between left and right, is always going to output a SIMD of 2. So now what we're basically doing is we're taking this 1-channel signal and turning it into a 2-channel signal. We are returning out times 0.2. Now, the next function is returning a 2-channel signal. So when it sends this 2-channel signal, I need to change that to out2. It's totally fine. It works. Now, notice that out worked, right? So we were sending a float 64 out this 2 channels. What it will do is it will automatically copy that value to the left and the right output here. But when we're using out2, this is a panned signal, so it's going to output the 2 channels panned. Okay, so let's hear that. Great. So it's taking that one sine wave oscillator and it's panning it left and right. Okay, so now we're going to use these this as a struct within a larger program. So right now it is the whole program, right? Os stuff is the program. So what we're going to do is we're going to change this from os stuff to partial. So it's going to be a partial in a harmonic series. So I'm just going to call it partial. And this partial is going to receive some arguments, and it's going to receive the frequency. This is going to be a float 64. You have to tell it what you're receiving. And the default, I'll give it a default of 100. So just it'll have a default value. It's also going to receive the mod frequency, which is also a float 64. And it will also have a default value, which is 0.25. And then it is going to receive a pan frequency, which is also a float 64. And it is going to have a default of 0.1. So notice that now these have red under them. It's because they already existed, so we can't declare them twice. Okay, so now we have this partial, and we need to make a struct that's going to call the partial, because this is no longer a viable graph. So we're going to make the struct, and this struct has to be called awstuff, because that's the name of the Mojo file. It is movable and copyable. Has a var, which is world, unsafe pointer, and world. And it's also going to have a var called partial for now, and that is a partial. So we declared partial up here, and we're using it down here. So because this is the main program, we can only, we need to make the init that is self world. I mean, we can just copy this, honestly, because it's going to be exactly the same. So it's an init function. It's going to make itself, but it's going to receive the world and assign that to the world. It's underlined in red because it's saying we haven't made self.partial yet. So we need to declare that or initialize that. Right, and the partial receives world, so in the init function. So when we make our partial, we have to send it world. Right? Hopefully that's clear. Okay, and this is the main graph, so it needs a next function that only uses self, and it's going to return the same thing as this is. So I can copy that, right? It's going to return a SIMD with float 2, float 64 and 2 channels. That's 98% of programs are going to do that. Okay, and so what we can do is we're going to say self, so out equals self.partial dot next, and let's give it, we can just call this, or we can give it values. So I could say 80, 0.2, and 0.07. Return out. So what's happening in this program? So the main program, MMMAudio, is looking at awstuff, calling the next function. Or when it initializes the program, it looks into awstuff. It knows that it's going to receive the world, and it's going to make a partial. It receives the world, makes a partial. The partial sends the world to partial. So then this gets declared, makes a partial. So the partial exists within awstuff. Now, when the next function comes, so this happens every sample, it says, okay, what am I going to do? I'm going to make an out variable, and I'm going to go to partial and get the next. So it's going to send the next value here. It's going to run this, and it's going to return out the output. It's going to return the output, assign it here, and then we're going to send the output to the operating system. So let's see if that still works. And it sounds exactly the same, or with different numbers. Okay, so now we have this program. We have a partial, and we've got stuff which contains the partial. So if we want to add more of these partials, we can do that. So we can have as many structs in our main graph as we want to. So I can make a second partial, var partial, and that's var partial 2, right? It's also a partial. We would have to declare it in here. Partial 2. And then we would also add it here. So first thing I'm going to do here is say that out equals, so I want it to start with 0 and then add each partial to it. So out equals simd dtype dot float 64 2. So I'm making a 2-channel simd, or simd of size 2, and then I am going to initialize every variable inside of the simd vector. It's a 2-channel simd vector as 0. So it means basically this is 0, 0. We could also just do this because it autofills the simd vector. Okay, so now we have, at the beginning of every next loop, we basically out is set to 0. And so what we're going to say is out plus equals, which means take out and then add the next value from partial. And let's copy that line. And out plus equals self.partial2 dot next. Let's make this the third partial. Make it go to a random, something like that. Bunch of primes. Great. So what we should now have is 2 notes, 2 pitches that are kind of floating around on their own in space. And let's hear that. Okay, so we could do this. We could do this forever, right? We could just keep adding partials. Another thing that we could do instead of just, so if I want, 11 partials, I don't want to keep adding 11 variables here. So instead of that, what I'm going to do is I'm going to make a list of partials. So I'm going to say partials is a list of partial, and then self.partials equals. Now this gets a little tricky. Mojo uses Python syntax. So what we can do is we can say partial world for in range 7. So what this is going to do is it's going to declare a partial for underscore in range 7. So it's going to put 7 partials into the list of partials. So yeah, you can also do that by declaring a list of partials and then doing a for loop to add partials into it. But this kind of does the for loop for you. Okay, so the other thing we're going to need now is a list of frequencies. List of mod frequencies. And that's going to be a list of float 64. So a list of floats. And what I'm going to do here is I'm actually going to fill the list with random numbers. So I'm going to say it's random float 64 between, let's say, 0.7 and 3 4 in range 7. Okay, so what's it complaining about? Forgot the S. Oh, random float 64, all kinds of syntax errors. Right, so now we're going to have 7 random values in a list. So now we have a list of partials, each with their own modulator frequency, and then let's give them all their own pan frequency. And we can just copy this. This is also going to be a list of floats. Self.panFreaks. And we're going to do the same thing, but maybe different numbers. So we're going to fill that with 7 random numbers between 0.1 and 0.3. So those are all moving pretty slow. Okay, so once again, our out starts in the next loop. So for each sample, the out starts at 0. And I'm going to say for I in range. And then we have a list of partials. We're going to say len partials. So this is a for loop over the list of partials. And out plus equals self.partials at I, because I is in the for loop. That's the iterator. So it's going to go through each of the partials. The frequency here is going to be the fundamental, whatever that is. Let's change it to 120 times I plus 1. So that'll go from 1 to 7. If we want them to be odd, we would do I times 2 plus 1. So 0 times 2 is 0, plus 1 is 1. 1 times 2 is 2, plus 1 is 3, etc. 2 times 2 is 4, plus 1 is 5. So we're going to do odd partials, and then we are going to do self.mod freaks at I and self.pan freaks at I. Okay, so now we should have 7 odd partials of a 120 hertz fundamental, each which should have its own pulse and will be panning individually. I'm going to turn this down a little bit. And that sounds pretty awesome. So the point here is we can have, every program needs to have this main struct, that's this graph struct. Within that graph struct, you can have as many unit generators or synths as you want. In this case, we have a list of synths, of 7 synths that are each of them 3 oscillators that are modulating each other in interesting ways.